Okay, so we're going to move on to the third part of the tutorial, so that's this U-band reduction step. Just for context, the reason why this is a separate set of steps to reduce U-band is sort of what I mentioned in the previous video, so that's that the APAS catalog does not have U-band magnitudes, so there's no way to calibrate the 0 point for our U-band images, so you have to do the separate set of steps in order to accomplish that. So what these do is these use standard fields that are taken on the same night at the same telescopes as your science images, and they use those to generate a local catalog of the supernova field that includes U-band magnitudes, so then we can use that catalog to calibrate the U-band and the other Landau bands as well. So I'm just going to copy this command to start. Oops, that's not what I want to do. I'm going to copy this command to start. Okay, so here's the first epoch that we've been reducing. I'm looking at the Landau filters, and then I'm getting all the standard observations that are associated with these filters. So again, it's standard observations on the same night and at the same telescope. And those are these L101 images. So all the Landau standard fields are called L something, like L101 or L94 or something like that. And you can see these images have not been reduced at all. This column is usually where the PSF is specified, so these don't have any PSFs. They don't have anything else as well. So the first thing we have to do is to reduce these standard images. And so I'm just going to copy some commands from the file. So we have to do the same thing as we did for our science images. We have to generate PSFs for them, and then also generate PSF magnitudes and 0 points as well. So in this command, I'm just selecting the standard observations and then running the PSF stage. The only thing I'm including is this extra argument, this max aperture argument. This is an argument that's been added relatively recently, and this value is the difference between PSF magnitudes and aperture magnitudes in the image. So ideally, you want this value to be small, close to 0. By default, this keyword is 0.1. And so if the difference between PSF and aperture magnitudes is bigger than 0.1, then the image gets rejected and its PSF doesn't get saved. So I'm increasing it to 0.2 because these first two images have aperture corrections slightly larger than 0.1. In principle, you can fix that by like adjusting the data max and data min values, but I'm going to sort of cheat and do it this way as an example. All right, so the PSFs have finished getting generated. So next up, you do the PSF mag stage. So you can see all the standard fields now have correct PSF files. These aren't X. This column isn't filled with X's anymore, so that's a good sign. And then we also have to run the 0 point stage, so that's CCAT, and then specify the field to the Landau field, because this is an object that has a Landau catalog. So before, for our science images, this stage didn't run correctly on the U-band images. It just said, cannot calibrate U. But now these first two images are the U-band images, and they're getting correct 0 points in color terms. So that looks like it all went well. Okay, so the name of the stage that is used to generate local U-band friendly catalogs is called local. So -s local, and then I'm also going to run it with the I for interactive. So this generates a bunch of plots. It generates plots for each filter. I'm going to skip to the B band because that's a little easier to explain. Um, okay, so in these plots, there's a lot of information going on here. In the top right panel over here, this is looking at B-band images. We only have the two, and the x-axis here is the star ID in the APAS catalog. The orange values are what the magnitudes for each of those stars are in APAS, and then blue is the new magnitudes that we're measuring for those stars given the 0 points that we measured for the Landolt fields. So ideally the blue and the orange circles should overlap. In principle, you see they're close, but they're not always perfectly identically overlapping. And it lists the median offset over here, which is 0.025 magnitudes. So if the median offset is very large, then that means that something has gone wrong. I'd say if it's larger than 0.1, then that's cause for a little bit of an alarm. Although APAS actually isn't always perfectly calibrated, so that might be a conservative estimate. But that could be an indication that you need to regenerate your PSFs for your standard fields or do something else to fix them. Or maybe throw out standard images that are not good, that are messing up your calibration. Okay, so this left plot is pretty much the same information as this right plot, but just plotted differently. Now it's looking at it by magnitude. You can, if there's any trends here that could be worrying, but you see they're all pretty tightly clustered around the median, so that's good. And then this bottom right panel, this is looking at it per image. And then now the black lines are individual star values and measuring their offset. So we only have two images. If you're reducing data for a full objects data set, you know, there might be 50 or 100 epochs. So then you'd have many images that you're medianing together to get better statistics. But okay, so this all looks normal. The median offset is pretty small. That's the main number that I check. So we'll continue. It does it again for V-band. So median is slightly larger, but still 5 centimags, so that's fine. And you can see it wrote a new catalog. So this is a Landolt catalog for the 17 CVV field, and we're going to use that catalog to redo the 0 point stage. So I'm going to select my Landolt fields, and I'm going to run the zcat stage, and then I can specify the catalog file. So I have a few of these because I've done this multiple times. But this is the catalog file that was just generated, so I'm going to use that catalog to redo the 0 point calibration stage. Okay, and now again, these U-band images, which before said, you know, we can't reduce, it's now using the catalog and the new 0 point to reduce them correctly. The other images were already calibrated, but just to be consistent, I'll rerun this with the -F, so that'll force them to all be calibrated to the same catalog to make sure I'm being consistent. So that's done. So the only thing to do after the zcat stage is the mag stage. So again, some of these images already have magnitudes, so I'm going to do -F to force those to have their magnitudes recalculated. And so great, these first two U-band images now have successful magnitudes, so that's good. And now if I run getMag on my epoch, this should pull up the full light curve, which now includes U-band images. And you can, you know, do the usual thing, point and click around to see how things are doing. So yeah, this means that the U-band was successful. these two images have consistent measurements. That's good. So it looks like everything went smoothly here. One other thing I want to mention is for the tutorial, I gave you a tarball, including those L101 standards. In principle, you'll have to download your own standards. And so I just want to give you an example of doing that. So I'm going to cd another directory, although it shouldn't matter too much. The way you ingest standards is with this lcogt ingest script. So the script has a bunch of arguments, which I can print with -h. You can specify the site and the instrument and what filters you want and all that good stuff. So just to give an example of a command that you would use. So let's say you have let's say you have images between these two epochs, and the syntax here is different. The start epoch is 2019-10-01, the end epoch is 2019-10-06, and this end is also exclusive, so apologies for the inconsistencies. And let's say you only care about, you only have science images taken at our Chile site at LSC. You only care about 1 meter standards, and you only need U-band stuff. You can specify that as well. You only want to download reduced data. You can also download raw data that hasn't been biased and flat fielded, but you probably won't ever want to do that. Standards all are under like a separate proposal. So if they're under the standard type, excuse me, this is observation type, not proposal. So we only want standards, and all standard images should be public. So we're going to download that. So this is just an example to show you the kind of command you would generate. Okay, so that command is finished running. So again, just to show you what a successful run looks like, it downloaded 8 frames, and all the standards were L94, that field, so it generated a new target for that, and then it ingested all the frames. So now if I want to look at that data, I'm looking for the L94 observations in this date range. And so these are my 8 new standard fields that I just ingested. And with this script, there's no like tarball that it gives you that you have to ingest. Just ingest them straight into the database for you. So again, in order to reduce U-band data, you need to download standard observations taken on the same night and at the same telescope as your science observations. You can do that with this lcogt ingest script, and then you have to reduce those standard observations, generate a new catalog, and then use that catalog to 0 point your Landolt images. And actually, one last thing that I want to say is that after you ingest new standard fields, you have to do the same thing we did at the beginning of the first video, or at the end of the first video, where you have to go into the database and specify that they're a standard, and then also move their Landolt catalogs to the correct place. So I bundled all the relevant catalogs together into the standard catalogs tar file. And so if you unzip that, untar that, then that has all the catalogs you need. And so you should move those to the, like we did for the L101 thing, copy those to LCOS under standard cat Landolt. So if I were going to use this object to reduce any data, I'd have to copy its catalog to this location.